What's going on, you guys? So today, oops, sorry about that. Today we're gonna do minimum depth of binary tree. So the idea behind this is we're given a binary tree. We're gonna find its minimum depth. Depth. The minimum depth is the number of nodes along the shortest path, from the root node down to the nearest leaf node. A leaf is a node with no children. So for example, here. Where this is depth 1 at the start, and then depth 2 here. So depth 2, depth 3. So we would return 2, because that's the minimum depth from the root to a leaf. And okay, so this is like a think if all of if 2, 3, 4, 5, and 6 were all just in a straight line, right? So they all just went down the same line. So that would be a depth of 5. So the tricky part comes in when we have to compare. So like, if we're thinking about it reasonably, we would say, with this one, the minimum depth equals 1 plus the minimum depth of 9 and 20, right? So let's see how that works. So the minimum depth of 9 is just 1. The minimum depth of 20 is 2. So it would be 1 plus 1 equals 2. So 1 plus minimum of root dot right root dot left, and the minimum depth of those two. But the issue comes in, let's think about this. So what happens when we do the, let's see, drawing whiteboard. Trying to get something so I can show you this. One edge case we need to handle. Okay, so let's see here. Okay, so we got 2, 3, 4, 5, and then let's see if I can. There we go. Okay, so so this way is null, right? So this is just null. So we would call min depth on 2, and then we would return 1 plus the minimum of min depth null on the left and min depth 3. So the issue is, what's the min depth of null? It's going to be 0, right? So this is going to be 0, the minimum of 1 plus 0 plus the min depth of 3. So the min depth of 3 is going to be 4, right? Right? So 1, 2, 3, 4. So the minimum, and then it just equals 4. So we're going to return 1 plus the minimum of 0 and 4, so 1 plus 0, or 1, right? So if we use this formula, it's not going to return the right value for when either the left or right node is null. What would be the correct one in this case? It would be, let's see. Let's just copy this. So if we added the min depth of null, it would just be 0. So that doesn't affect anything. And then if we add the min depth of 3, it would be, let's see, 0. So the depth of this 1, 2, 3, 4, 4. So we would get the right answer if we just, so the first case, we take the minimum of right and left. This case, we just add right and left. So we need to account for that scenario. So we'll say if left or right are null, so root.left equals null, or root.right equals null, we'll do 1 plus left plus right. In this case, we'll do we'll do the minimum. We'll do the minimum when left and right are not null. And so let's see if that will handle all edge cases. Oh, and also if root is 0, we just want to, if root is null, we just want to return 0. Okay. Let's think here. So var right equals min depth root.right. Do the same for the left. We'll say if root.left or root.right equals null. Sorry. We're going to return 1 plus right plus left. Otherwise, we'll return the minimum of right, left, 1 plus the minimum. Okay. Let's see if that works. Oh, misspelling there. Okay, you guys, so there you have it. That's a recursive solution. Let's think about space and time complexity of this guy. So it's not very good. So we could definitely do better. So time complexity, let's think. It has to touch each node in the tree. And do we touch it more than once is the question. I don't believe we do. We only touch each node once. So it should be O of n time for the number of nodes in the tree. And space complexity, O of n space complexity, because we're calling min depth n times, where n is the number of nodes. We have to call it on every single node. And so if we did an iterative solution, then we could take the space from O of n down to O of 1. And so you would think about there either a depth first search approach or breadth first search. All right, you guys, so that has been minimum depth of a binary tree. Stay tuned for the next one. See you guys.